welcome to Clash Course. We're your hosts, Emily Harris.
And Anne McHale, and today we'll be talking about the famous scientists through time.
Let's start off going all the way back to the great year of 460 BC, the time of the Greek philosopher Democritus. Democritus was the first to propose the atomic theory. He knew that if a stone was divided in half, the two halves would have essentially the same properties as the whole. Therefore, he believed that if you keep dividing the stone into smaller pieces, like this, even though this is not stone, it's a piece of paper, the pieces would eventually become invisible. He called the smaller pieces of matter atomos, which means invisible in Greek. He theorized that these atoms were specific to the objects that they made up. He also believed that each atom was a different size and shape, as well as always in motion. So when these tiny little guys collide, they either rebound or stick together. If these atoms stuck together, they would create a change in the matter around them. Though this theory was remarkable, it was turned down by fellow philosopher Aristotle, and the atomic theory was forgotten about for about 2,000 years.
Which brings us to the year 1803, when John Dalton proposed the modern atomic theory. After piecing together what was known about chemistry, Dalton contained 5 basic assumptions within his theory. The first being that all matter contains tiny particles which are called atoms, a theory which was generally agreed upon by Dalton and others. Another hypothesis of the theory, based upon the law of conservation of mass, is that atoms are indestructible and unchangeable. Dalton also suggested that all elements can be categorized by the weight of their atoms, meaning every element of oxygen would have identical weights, but atoms of different elements, like oxygen and mercury, are not the same. He also suggested that in chemical reactions, atoms combine in small whole number ratios, which was indicated by the results of chemical reactions performed by him and others. The final observation of Dalton's atomic theory is that when elements react, their atoms may combine in more than one whole number ratio. Following the proposal of this atomic theory, Dalton was met with the general agreement from the scientific community and has held up well ever since, with some modifications to the original proposal.
Let's fast forward to the year of 1897 when J.J. Thomson discovered the electron. This all happened because of the device we know as the cathode ray tube. He saw that the rays coming from the tube were negatively charged. He realized that the model of an atom at the time did not account for the negatively or positively charged particles. Therefore, he created what we know as the plum pudding model. This is called the plum pudding model because, well, it looks like plum pudding. The electrons represented the raisins, while the dough represented the positive charge. This model did explain some of the electrical properties, but because of the electrons, it failed to recognize the positive charge particles.
Which brings us to the year of 1911, where Ernest Rutherford, a former student of J.J. Thomson, proved the plum pudding model incorrect. Rutherford discovered this through an experiment involving alpha particles. He aimed these particles at substances like gold foil and recorded where they struck as they passed through the substance. While most particles passed through unaffected, some were deflected off at an angle and a few even darted straight back. These results led Rutherford to discover that atoms are composed of a positively charged nucleus surrounded by negative electrons.
Now that it's been discovered that the negative electrons surround the positive nucleus, Niels Bohr established a new concept of the structure of the atom in 1913. Following in the footsteps of his mentor Rutherford, Bohr proposed that electrons are arranged in concentric circles around the nucleus, closely resembling our solar system, hence why it's known as the planetary model. This model can be summarized into 4 basic principles. The first being that electrons occupy only certain orbits around the nucleus. Those orbits are stable and are called stationary orbits. The model also shows that each orbit has an energy that comes along with it, and that energy is absorbed when an electron jumps from a lower orbit into a higher one, and energy is emitted from an electron that falls from a higher orbit to a lower one. And finally, this model showed that the energy and frequency of light emitted or absorbed can be calculated by using the difference between 2 orbital energies.
And the final scientist we'll be talking about today is Erwin Schrödinger, an Austrian physicist who took the Bohr model one step further in 1926. Schrödinger created the quantum mechanical model, in which used mathematical equations to predict the likelihood of finding an electron in a certain position. Unlike the Bohr model, Schrödinger predicts the odds of the location of an electron rather than trying to determine its exact path. His model is portrayed as a nucleus surrounded by an electron cloud. Wherever the cloud is most dense is where he determines it's most likely to find the electron, while the less dense areas of the cloud are less likely to be the location of the electron. Schrödinger's model has introduced the concept of sub-energy levels.
Thanks for tuning in for another episode of Clash Course. I'm Emily Harris.
And I'm Ann McHale.
Thanks for watching, and don't forget to be cool.